Okay, this is a video lecture for Math 181, and this video lecture is for Wednesday, April 15th. And the topic today is the area problem. We're now getting into chapter 5. And I would say one of the two fundamental problems in calculus is how do we calculate the area under a curve? The other big problem is how do I calculate the slope at any point along a curve? And we've actually already done that problem. This is the second big problem in calculus. How do we calculate the area under a curve? So let me draw a curve here for you guys. As an example, let's say we had the following curve. And we're interested, we had 2 points, A and B, here. And what we're interested in doing, what this problem involves, is we're interested in calculating the area under this curve. Now, how do we do that? Now, you guys have calculated areas before. You've calculated the area of a rectangle. We know how to do that. The area of a circle, the area of a triangle. But this is more complex. We have some curve, some function, and how do we find the area under there? The key to finding the area, the key in calculus, I can't emphasize this enough, is what we do is we divide this region into a series of rectangles, and so on. That's a rough diagram shown there, but what we do is we divide this region into rectangles, and then we calculate the area of each rectangle, and then we add up all those areas to get the total area under the curve. Now you can see here that there will be some error in this calculation, and I want to talk more later about how do we deal with the error there's a difference between the actual area under this curve and the area of all these rectangles, and so we'll talk about that. But that's the gist of it. It's the key idea. We divide the region into rectangles. So what I want to do is consider a specific example, and we'll see a little more precisely how this works. And the example I want to consider is the function f of x. So here's an example. F of x equals x squared. We're going to consider this function, and we'll consider it in the region from 0 to 1. So what I'm going to do is create a graph of this function in this region. And this is obviously a parabola, and it's growing like this. We're going to pick 2 points. Our final endpoint is 1. We're going to start at x equals 0. We're going to go to x equals 1. And what I'm going to do here, I'll use a different color to indicate this. I'll use red to indicate this. What I'm going to do is I'm going to divide this region up into rectangles. Okay, so what I'm going to do is put points here. This is 1/2. This is 1/4. This is 3/4. And what I'm going to do is divide this region up into rectangles. And these are my rectangles. One rectangle looks like this. One rectangle looks like that. Another rectangle looks like that, and my final rectangle looks like that. They should all be the same width, it's just imperfection in the diagram. So what I'm going to do is I'm going to approximate this curve as a series of rectangles. And I'm going to approximate the area under this curve from 0 to 1 I'm going to approximate it as the sum of the area of these 4 rectangles. Okay, let's see how this works. Well, as you guys know, the area of a rectangle is base times height. Okay? So let's label these. This is 1, 2, 3, 4. The area of rectangle 1 is going to equal, the width here is 1/4, times the height. Now, what is the height here? Well, the answer is the height is this function evaluated at the point x equals 1/4, right? The height here is the height here. This height is the y value of this function evaluated at x equals 1/4. In this case, so this is 1/4 times f of 1/4. Well, here we know the function, so it's 1/4 times, we're going to plug in 1/4 for x and square it, okay? And this comes out to, if you guys calculate this comes out to 1/64. So this first rectangle has an area of 1/64. And then I calculate the rest of the rectangles, okay? The second one is the same width of 1/4. Now now, to evaluate the height of this rectangle, I plug in x equals 1/2. Okay, so I get 1/2 squared. and this comes out to 1/16. So the area of this second rectangle is 1/16. And then the area of the third rectangle, same width of 1/4. In this case, I'm going to plug in the point x equals 3/4 to get the height of this rectangle. And so this is 3/4 squared, and this gives us 9/64. And then for the final rectangle has a width of 1/4, and I plug in x equals 1 to get the height of this final rectangle. So I get 1 squared. Okay, and this equals 1/4. And now if I add all these up, areas up, the total area, I'll let you guys verify this, the total area is 0.46875, okay? Now, let me comment about this. This is the area of the sum of these four rectangles. Now, you might at this point say, well, wait a minute, that's all well and good, but there's obvious differences here. In fact, I'm going to put them in blue. You know, all this area right here, right, is extra area, right? It's extra area. So this area, yeah, it's the area of the four rectangles, but is it an accurate representation of the area under this curve? Well, it's probably not too accurate. It looks like it's going to be an overestimate of the area. So you might balk at that, but let's just run with this idea of using rectangles. And what I'm going to do now is I'm going to switch the scenario, and I'm going to consider the same curve, but we're going to use a different set of rectangles. So let's do that. I'm going to erase this. Actually, you know, I'm going to use this. I do have enough room to do this. Why don't I use a different color? No, I'll just erase it. Just debating how to present this best. What I want to do is consider the same curve. Okay, so I have my parabola that looks like this. It's growing, and I have my two endpoints, 0 and 1. Then now I'm going to again divide this region into 4 parts. That's 1/4. But this time, here are the rectangles I'm going to use. I'm going to use different rectangles. In this case, I'm going to use these rectangles. Let's see. And there's a rectangle right there. So in this case, I'm going to use this set of rectangles where the height of the rectangle for each interval, in the other case, the height of the rectangle was determined by the right endpoint of my interval. But in this case, I'm going to use the left endpoint of my interval to define the rectangles. Okay? And now I'm going to calculate the area in this case. Let's label these. This is my first rectangle. But you see what I'm doing here? The height in the previous example, the height of the first rectangle was dictated by the value of the function at 1/4. Whereas now the height of the rectangle, the first rectangle, is dictated by the value of the function at x equals 0. So these are my 4 rectangles. And I'm going to calculate the areas of these. The first rectangle has a width of 1/4, and now I plug in x equals 0 as to get the height of the rectangle. So 0 squared, this just equals 0. I'm going to calculate A2, which is a width of 1/4 times 1/4 squared. This comes out to 1/64. I'll let you guys verify this. A3 comes out to 1/4 times 1/2 squared, which is 9/64. No, excuse me, is that right? Oh, no, excuse me, 1/16. My bad. 1/16. And then A4 is 1/4 times 3/4 squared equals 9/64. And now I add all these areas together, and the total area comes out to, let me write this down here, you guys can verify this, 0.21875. Okay, this is using left endpoints. In the previous case, I didn't write it down, but the previous case was using right endpoints. Okay, now you might stop here and say, but wait a minute. This area estimate is an underestimate of the area because I'm missing all these regions, right? I'm missing all those regions. You know, the rectangles fail to to get the area of these missing regions, so this must be an underestimate, which is true. But one thing is for sure, I now can constrain the area under the curve. So I know the true area under the curve has to be between these two values, right? It has to be between 0.21875 and it has to end up 0.46875. The area of under the curve has to be between these two values. Now you might say at this point, well, that's a pretty wide range in the area. Did this really help me estimate the area under the curve? Well, the answer is we can do a lot better than this. And hopefully you guys see the way we can do better. If you want to do better than this, if you want to constrain the area more narrowly, what you do is you use more rectangles. Use more rectangles, okay? Use 8 rectangles, use 10, use 1,000, okay? And I'm going to write some data down for you guys. If I use more rectangles, okay, instead of using 4 rectangles, if I use 10 rectangles, I constrain the area as such. If I use 10 rectangles, I've constrained the area. Now, it's still a wide range, but it's better. If I use 1,000 rectangles, okay, I constrain my area by this amount. 3328335 less than area less than 0.33335. There's actually one digit difference here. Now, let's say I use 1,000 rectangles. So instead of approximating the area under the curve by 4 rectangles, I use 1,000. Now I do a lot better, right? I have very narrowly constrained the area. In reality, in fact, the area in this case equals 1/3 exactly. Okay. If you use millions and millions of rectangles, you get a more accurate area, and you get 1/3 exactly. Now you might also say at this point, though, well, that's well and good. I could use 1,000 rectangles, but this would become a very complicated calculation if I use 1,000 rectangles, and that is true. But you can use a computer to do it. Later on, and just to tell you guys this, no one in calculus actually estimates or calculates the area under a curve by doing this area calculation. So just as with derivatives, this is kind of a baby version to get us so we understand the concept behind calculating areas, and then we're going to later use something called an integral to actually do the area calculation, and it's not super hard. It's actually pretty easy. There's a quick way I can do this, but right now we're learning the hard way. Not the hard way, it's just the more theoretically valid way to do this, so you guys understand the theory behind this. But basically the idea again is divide a curve up into a series of rectangles, calculate the area of each rectangle, add them up, and you get the area under the curve approximately. The more rectangles you use, the better your area estimate is. Okay, I want to make this a little more general, so we're going to step out of this specific example. And this board is not erasing fully, and I'm not sure why that is, but it's getting clean enough for our purposes. So what I want to do is consider a more general example. So more generally, let's say we have some curve. And let's say it's some curve S. So let's say this curve goes like this, goes up like that. This is some curve. We've got 2 endpoints, A and B. And we're interested in the area between these 2 points. What we're going to do is we're going to start dividing. We're going to divide this region into rectangles. Okay? So I could have a rectangle here, and a rectangle here, and a rectangle here, and let's make these the right endpoint heights. So this would be like this would be like this would be like this, and so on. And then so I'm going to divide my region up into pieces. This point I'm going to call x1, this is x2, this is x3, this is x4, and so on. Okay? And what I want to do is and this is the curve S. Let's call this a curve S. Okay. And then I can ask myself some questions like, what's the width of my rectangles. The width is called delta x. So this width right here, the width of each rectangle is called delta x, okay? Delta x, if you want to calculate delta x, it equals b minus a over n, where n is the number of, rectangles. So if you decide to use 100 rectangles, the width of each rectangle is the right endpoint minus the left endpoint of your whole interval divided by the number of rectangles. And then if we talk about intervals, there's various intervals here. And intervals are x0 to x1, that's one interval. The next interval is x1 to x2, and so on. Don't worry too much about that, but these are just dividing this up into different intervals. And then we can actually write down the different values of x1. Like x1 will equal a plus delta x. So x1 is equal to a plus 1 width of a rectangle. x2 is equal to a plus 2 times delta x. So x2 is equal to a plus 2 widths of a rectangle. And x3 is equal to a plus 3 delta x. Okay, and so on. We can go down the line to get each value here at which we're evaluating. So what are these x1s and x2s? They're basically the values of x which determine the height of our rectangles for which we're going to evaluate our function. Okay. And then finally, the area of this, I'm going to use r sub n here. What is the area of all these rectangles? Well, it's just the sum of the rectangles. It's the sum of the areas of the rectangles. What's the area of the first rectangle? Well, it's the width, delta x, times the function itself. This is some function f of x, times the function evaluated at x1, plus the width of the second rectangle, which is delta x, times the function evaluated at x2, plus plus delta x times the function evaluated at x at b, right? Should I get that right? Or x sub, it is b, but let me call it x sub n. X sub n is basically the last point along this region here. So what I'm doing is the area under the curve, which I'm calling r sub n. Why r sub n? Because I'm using right endpoints. So the r stands for right. So I'm using right endpoints. The area under this curve is approximately equal to the sum of all these rectangles, starting with the first area of the first rectangle plus the area of the second, and so on, to the area of the last rectangle, the nth rectangle. Okay, and I used r sub n because r indicates I'm using the right endpoint of this interval to evaluate the height of my rectangle. And n stands for the number of rectangles I'm using. So the more rectangles I use, if I use 1,000 versus 100, the more accurate my area estimation is. Okay, so let me now give you a definition here. And this might seem kind of theoretical, it might seem a little scary, but we'll do an example problem, and you guys will see exactly how this works. It's not super scary. Let me get another black pen here, so it's kind of bad on me. Okay, so let's talk about some definitions here. So it turns out we're going to define the area under a curve as the limit as n goes to infinity of r sub n. Now think about this. We're estimating the area under a curve by dividing it up into a series of rectangles. The more rectangles we use, the more accurate the area estimate is. If we, in the limit as n goes to infinity, in the limit as we use an infinitely large number of rectangles, our estimate of the area will become no more an estimate, it will become exactly the area. So to get the exact area under a curve, we take the limit as n goes to infinity of the sum of all of our rectangles. So in other words, we get the limit as n goes to infinity of delta x times f of x sub 1 plus delta x times f of x sub 2 plus plus delta x times f of x sub n. The means go on for all the rectangles. But now there's a shorter way we can write this. We can write it as the limit as n goes to infinity. We're going to use a summation sign. So hopefully you guys have seen summation signs recently. And we're going to basically write this in a more compact version. So the limit as n goes to infinity of the sum of the function evaluated at each point of evaluation times the width, delta x. Okay? And so this is the width of a rectangle. These are the different heights of the rectangle evaluated at our different points that we've divided our interval into. We're summing all the areas of those rectangles up, taking the limit as n goes to infinity, and this becomes exactly the area under the curve. Okay, one point to make here, we can use different endpoints, we can use different sampling points. Again, this might be a little confusing theoretically, but when we do an example problem, it'll make sense. We can use different sampling points. So we also, this is a right endpoint, where we're evaluating the height of our rectangles at the right endpoint of each interval. We also could use the left endpoint. In this case, our area equals the limit as n approaches infinity, of the sum of I equals 1 to n. Only difference is we're going to do xi minus 1 times delta x. So what this indicates is instead of evaluating the height of our rectangles at the right endpoint of our different intervals, we're going to evaluate the height at the left endpoint of our different intervals. Or you could even do, another example is to do a midpoint. You might say to yourself, well, I would like to evaluate the height of my rectangle at the midpoint of each interval. In that case, what you could do is do this. And we're going to do it like this, I1 to n. And now we're going to evaluate the height of our rectangles at the midpoint of each interval times delta x. This is often referred to as L sub n, the limit. L sub n, you can refer to this as the limit of m sub n. So L sub n stands for we're evaluating at the left endpoint of our intervals. M stands for evaluating at the midpoint of our intervals. So again, this is kind of theoretical, but it's important. The area under a curve is defined as, so you break a curve up into a series of rectangles. The exact area under the curve is equal to the limit as the number of rectangles goes to infinity. As the width of each rectangle shrinks to 0, we're taking the limit of the sum of the areas of all those rectangles. This is the key to the second problem, important problem in calculus. What we're going to do now is we're going to do an example of this, of a simple problem using these principles we've just talked about. So let's do an example. And in this example, we're going to consider the function f of x equals e to the x, the simple exponential function. And we're going to be interested, we're going to estimate the area between x equals 0 and x equals 2. We're going to estimate the area between x equals 0 and x equals 2. So if we graph this function, we know, just a rough sketch, we know this function is going to grow exponentially like this. We're interested in the region from x equals 0 to 2, and we're interested in estimating the area under this curve between these 2 points. We're going to estimate the area under this curve right there. And we're going to do it 2 ways. One way we're going to use the right endpoints. So we're going to use 4 rectangles to estimate the area. In part A, we're going to use the right endpoints. We're going to use the right endpoints. So if we divide this interval up, right, into 4 parts, we're going to get, this is a 1, this is 1/2, and this is 1.5. So we're going to divide this interval into 4 parts and use 4 rectangles. Okay, what I'm going to do is calculate R4, which is the sum of the areas of our 4 rectangles. So for the first rectangle, right? The first rectangle, using the right endpoint, we know that the width of our rectangles is 2 minus 0 divided by 4, because we're using 4 rectangles. This is 1/2, or 0.5. So each rectangle has a width of 0.5. If we were to draw in our rectangles here, draw them in, we get something like this. That's one rectangle, then we get that rectangle. Oops, that came a little bit off. Then we get this rectangle, and finally this rectangle. So we have our 4 rectangles. We're going to estimate the area here. The first rectangle has a width of 1/2 times a height. What's the height of this rectangle? It's the function evaluated at x equals 1/2 is the height. So this is e to the 1/2, or 0.5 power. The next rectangle has a width of 1/2. What's the height of the next rectangle? It's the function e to the x evaluated at x equals 1. So this is e to the 1 plus 1/2 times the width of the third rectangle is 1/2 times the function evaluated at x equals 1.5 plus 1/2 times the function evaluated at x equals 2. Okay, and you guys can check the arithmetic here, but if you guys calculate this, you should get 8.119. Okay, so the area under the curve e to the x from 0 to 2 is 8.119. Okay, now is that accurate? Well, not too. It's probably not too great. It looks like it's an overestimate. This is an overestimate. But if we use more rectangles, we could get a more accurate estimate. Now, I want to do a second part to this problem. The second part is, let's do the same thing, but let's use the midpoint. Let's use the midpoint to evaluate the heights of a rectangle, the midpoint of each interval. Well, the midpoints of each interval, if you take the midpoints, they're going to be 0.25. The next midpoint is 0.75. The next midpoint is 1.25, and the final midpoint is 1.75. Okay, so we're going to use the midpoints of these intervals and estimate the area that way. In this case, we're going to call this M4. M for midpoint, 4 for using 4 rectangles. And now the width of my rectangle remains the same, but now to evaluate the height of my rectangle, I'm not using the endpoint, I'm using the midpoint of that interval. And that midpoint, the y value of this point here is e to the 0.25. Plus the next rectangle has a width of 1/2 times e evaluated at the midpoint of this interval, which is 0.75, plus 1/2 times e evaluated at the midpoint of this interval, which is 1.25, plus 1/2 times the height of this final rectangle evaluated at the midpoint, which is e to the 1.75. And again, I'll let you guys check the arithmetic on this. This comes out to 6.323 as the area here. Okay, so this was probably an overestimate. It's hard to know if this is underestimate or overestimate. It turns out using midpoints is always a better method. Oops, I shook the camera a little bit. But anyway, and it stopped the video. No, it did keep it going. I kept the video going. My bad. Okay, so is this an overestimate or underestimate? I don't really know. But it's probably a decent estimate. Let me just make sure the camera's still working. I think it is. I'll assume it is. So this is the estimate of the area using the midpoint. And this is probably a more accurate estimate, but it's probably not exactly accurate. To do better, you'd want to use more rectangles. But this is a simple example problem using this method of rectangles to estimate the area under a curve. And we could have also done the left endpoint, which would have been an underestimate. But anyway, I'll leave that if you guys want to practice it. This concludes the video. I know that was a lot. It was kind of a whirlwind tour of areas. Again, I'm trying to keep the video length reduced. I will see you guys on Wednesday.